During this video, we are going to take a deeper look at periodic trends. A trend is a pattern. And remember, periodic means repeating. So periodic trends are repeating patterns. Let's start with an obvious pattern that serves as the basis for organizing the periodic table. If you move across the period, which if you remember is left to right across the table, the atomic number increases. The same is also true for the atomic mass, with only a few limited exceptions, like the one from argon to potassium, cobalt to nickel, and tellurium to iodine. Down a group or family, the atomic number and atomic mass always increase. Here is a quick review of the classes of elements. Remember that metals are on the left side of the table and nonmetals are on the right side of the table. Metals and nonmetals are separated by the metalloids, which form a staircase between the two. Hopefully you have drawn this staircase onto your periodic table. After reviewing the classes of elements, it should make sense that metallic properties of the elements decrease as you move left to right across the period. Potassium is more metallic than iron. Iron is more metallic than bromine. Down a family or group, the metallic properties increase. Barium is more metallic than magnesium. Just what does it mean to be metallic? Remember, metals will lose electrons when they react. Metals are shiny and pliable. So when I tell you that iron is more metallic than bromine, that should make sense. Iron atoms lose electrons when they react. Iron is shiny and can be bent into shapes. Bromine atoms are in the liquid state at 0 Kelvin, so not very shiny or durable, and bromine atoms strongly resist losing electrons. We will explain that further down the road. Reactivity is also a periodic trend. This trend is specific to the class of elements, so we want to keep that metalloid staircase in mind. The reactivity of metals decreases as you move across the period, and the reactivity of metals increases as you go down a family. If we follow these trends, that would make francium the most reactive metal. Let's move to the right side of the table and consider the nonmetals. Starting at the staircase, the reactivity of nonmetals increases as you move from left to right across the period. Looking down a group, the reactivity of nonmetals decreases. This means that fluorine is the most reactive nonmetal. Now keep in mind that noble gases are inert. They do not react. So I am ignoring those elements when discussing reactivity. We will talk about why noble gases are unreactive here in a second, so just be patient. As we discussed families in the last video, I pointed out the trend in valence electrons. Remember, valence electrons are the electrons in the outermost energy level of an atom. Well, the number of valence electrons increases by 1 as you move across the period. We will ignore the transition metals for now. There's no trend down a family. All the group 1 alkali metals have 1 valence electron. All the alkali earth metals in group 2 have 2 valence electrons. Skipping the transition metals, all the atoms in the next group have 3 valence electrons, and then 4 valence electrons, and then 5 and 6 valence electrons. The halogens in group 7 have 7 valence electrons. Finally, all the noble gases in group 8 have 8 valence electrons. By now, I really hope your periodic table looks like this. If not, take the time to do it now, which means you'll probably have to pause the video. Now let's look at the trends that we graphed for the periodic trends activity, starting with atomic radius versus atomic number. Atomic radius is basically the size of the atom. The trend across the period should be easy to see from this graph. Period 1 is represented in red, period 2 in green, and period 3 in blue. You can see for each of the periods, atomic radius decreases across the period. That means that atoms get smaller in size as you move left to right across the table. The trend down a family might be a little easier to see if you label the graph. Hydrogen, lithium, and sodium are all in group 1. If you look at these 3 points, you can see that the atomic radius increases as you move down a family. The same is true for group 8 if you compare neon to argon. Atoms get bigger as you move down a group. Ionization energy is the energy required to remove an electron from an atom. You can see the general pattern for this trend is that ionization energy increases as you move from left to right across the period. There are a couple dips, but for the most part, the trend is more energy is required to remove an electron from an element on the right side of the table. Now, if you have been paying attention, this should make sense. Nonmetals are on the right side of the table, and nonmetals want to gain electrons, not lose them. Therefore, the energy required to remove an electron should be higher for a nonmetal. The opposite is true for metals on the left side of the table. Metals would rather lose electrons, so the ionization energy for a metal should be low. Once again, the trend down a family will be easier to see if we label the elements. Looking at the elements in group 1, you can see that the ionization energy decreases down a group. You can see that trend is also true for neon and argon in group 8. So less energy is required to remove an electron from an element further down a group. The trend of boiling point versus atomic number was not so clear to see, partly because the large differences in boiling point made scaling the graph difficult. Labeling the graph may make it easier. You can see that boiling point increases across the period for metals. Then as we switch to nonmetals, the boiling point decreases significantly. In general, for nonmetals, boiling point decreases as you move across the period. So the trend for a row on the periodic table would be the boiling point increases for metals and decreases for nonmetals. Down a group or family of metals, you can see the boiling point decreases. Look at lithium and sodium here. However, for nonmetals, the boiling point increases down a group. Look at oxygen and sulfur here. The trend for boiling point is definitely more difficult to see, but there is no doubt a pattern exists. There is one more trend I want to discuss, and it deals with valence electrons. If you recall, valence electrons are electrons in the outermost energy level of the atom. The number of valence electrons determines the chemical properties of the atoms because they are the only electrons that participate in bonding. The shared chemical properties of the elements in a group The preferred number of valence electrons for an atom is 8. Atoms with 8 valence electrons do not react further because their outer energy level is completely full of electrons. Atoms react in order to achieve a full valence shell. They could either gain electrons, lose electrons, or share electrons in order to achieve 8 electrons in their outer energy level. But we will talk more about that next unit. Noble gases are unreactive because atoms of the elements already have 8 valence electrons. There is no need for an atom to react if the atom already has a full valence shell. So the final trend we are going to talk about involves an atom losing or gaining electrons. When a neutral atom gains or loses electrons, the atom becomes charged. A charged atom is known as an ion. There are 2 types of ions. Nonmetals will gain electrons. Remember, electrons are negatively charged. So when an atom gains electrons, it gains negative charge. Ions with a negative charge are called anions. Metals tend to lose electrons. Since electrons are negatively charged, losing them would result in more positive protons in the nucleus than negative electrons in the electron cloud. Therefore, metals form positive ions called cations. This is easy to remember because cations are positive. That's right, cations are positive. Yes, positive. Now, let's put this on your periodic table. If you labeled your table as I showed you, you should have some space above where you put the valence electron labels. Okay, metals want to lose electrons. This means the alkali metals in group 1 will lose this 1 valence electron. Losing an electron would result in the formation of a positive ion. So all the alkali metals form a +1 ion. Write +1 above group 1 on your table. All alkali earth metals will lose 2 valence electrons and form +2 cations. Write +2 above group 2. The same process would continue for group 3, so write +3 above group 3. All the nonmetals except the noble gases will gain electrons. The halogens have 7 valence electrons, but they all would like to have 8. So all the halogens will gain an electron. they will gain a negative charge. Therefore, the halogens form -1 anions. Family 6 atoms will gain 2 electrons to achieve a full outer energy level. So these atoms form -2 anions. The trend continues for family 5. These elements will gain 3 electrons to form -3 anions. I hope you were writing these ion charges on your table. All right, the elements in the group with carbon are stuck in the middle. Do they form +4 cations or -4 anions? Well, it turns out they could form both. So above group 4, write +4 and -4. Please make sure your final labeled periodic table looks something like this. I'm sure your head is spinning with all of this periodic trend information. So until next time,